Welcome back. In the last video, we visualized one of our samples of data, a lovely image of pizza. This might change because of randomness, so don't worry if you don't get the same one, because our data is going to be loaded randomly. We just needed an example to look at. But now let's start to move towards recreating the Vision Transformer architecture. So we're going to spend the next couple of videos, I'm not sure how many, kind of breaking this down to give an overview, and then we're going to start writing code to sort of match that overview. But we've got a few pieces of the puzzle here, and we're going to be jumping back and forth. Of course, the whole paper is pieces of the puzzle together, but the main ones we're going to be concerned with is figure 1. So this is the visual overview of the architecture. And then we have a method here. So section 3.1, if you want to read anything in the paper twice, I'd recommend reading section 3.1. So this is text. Then we have 4 equations. So these 4 equations make up each of the layers in mostly the transformer encoder layer over here, but they make up the Vision Transformer. We're tying everything together. It's kind of a little bit higgledy-piggledy, but that's all right. We'll bring it together. 4 equations. And then finally, we also have table 1. So I love how they're all on different pages as well. Now, we're going to be focusing on building VIT base, which is the smallest version of the Vision Transformer. But we're going to build it in a way that if we wanted to increase the hyperparameters, these values here are hyperparameters. Why are they hyperparameters? Because we can set them ourselves. If we wanted to increase from VIT base to these larger versions, we could do that. So let's jump back into the keynote. Yeah, that's where we want to go. What's the next slide? Oh, I should have shown you this before. But this is table 3, just extracted from the VIT paper. And a little treasure here, we've got batch size 4096. This is what machine learning paper replicating is all about. It's treasure hunting. We need a treasure hunt for the right steps and ingredients to build our Vision Transformer. And then there's an image size 224, 224. So height is 224 and width is 224. And there's a whole bunch of different details. We're focused on this one. VIT should be a B there, a patch size of 16. We'll get to all of this. We're not training on ImageNet because we haven't downloaded ImageNet, and we're going to do a smaller version of these parameters. But if you'd like to do more research, you're more than welcome to figure out what these are. But here's how I break things down with almost all kinds of neural networks, machine learning models, whatever you name it, deep learning architectures. I break it into inputs, outputs, layers, and blocks. So what are the inputs to your layer to generate some outputs? And now often, or very usually, a layer contains some kind of function to manipulate an input. So an input here could be an image, it could be some text, but not in image or text form, it's in numerical form. And it goes into a layer and it gets manipulated by some internal function such as attention. Now this is the self-attention formula, which is what the Vision Transformer and all transformers usually use. Is it takes 3 inputs, a query, key, and value, performs a softmax on the query times or matrix multiply the key transposed over the embedding dimension. We're going to see all these later, the square root of the embedding dimension, times V, which is the value. And a little bit confusing is that sometimes query, key, and value can be all the same, hence the term self-attention. Now, if we look up self-attention formula, we might find it, images, there we go, something like that. Basically the same, yeah, there's the same formula as we've got in the keynote, same formula here as here. And if you want to research, you can go explained. We're going to focus on writing PyTorch to build this. So let's jump back. We're breaking this down. So that's a single layer. A single layer has some inputs and some outputs, and the inputs get manipulated by some sort of function. An example function could be attention, and in the case of the Vision Transformer, this is actually used in the architecture. Then we build it up from a layer to a group of layers into a block. So a block is a stack of layers, but if a single layer takes inputs and outputs, then a block also takes inputs and outputs because a block is just a stack of layers. Now, the number of layers in here is arbitrary. I've just put 3 because it looks pretty, but you could have 5, you could have 10, you could have 2. And if we jump back into the Vision Transformer, we're going to be doing a fair bit of jumping around, but we can handle it. A transformer encoder block might have 1 norm, multi-head attention, 2, 3, 4 layers. So this is a block of 4 different layers. But if we go back here, again, the number of layers in a block can generally be arbitrary. And then if we go again, we have inputs. We want to stack multiple blocks on top of each other. We get a model. So a model is a stack of blocks, but the same principle remains. And we've seen this. We've seen this by building neural networks throughout the entire course, is that we have some sort of inputs. In our case, it's going to be images. And we want our outputs to be labels or classification labels, such as pizza, steak, and sushi. But these inputs could be almost anything you could imagine in machine learning, as long as you can define your outputs. Now, the whole goal is to build up layers, blocks, and a model to map from the inputs to the outputs. And the important thing, behind the scenes, the model learns the mapping from the inputs to the outputs. So even though we've got quite a task in front of us, as 22 pages of research code, the same premise remains. We have some sort of input, we have some sort of layers and block combination, and then we have some sort of output here. This is a block. We've got L times X. Then we stack a number of blocks on top of each other into this section here, and we have an overall model. So this is kind of what we're going to be using as our high-level overview. We have inputs, some data, some outputs, some manipulated data, layers, a function to manipulate an input, and a block, which is a group of layers, and then a group of blocks makes up our model architecture. So let's go and write this down. This is 3, which is replicating VIT overview. So I'm going to write, looking at a whole machine learning research paper can be intimidating. Thank God this is not a spelling bee. We're focused on writing code here. So, in order to make it more understandable, we can break it down into smaller pieces. That is the key there. We break it down, we break the paper down into smaller pieces. We go treasure hunting. We find the treasures in here, we find the different layers, we find the different blocks, we stack them together like Legos to build a vision transformer or whatever architecture you're working with. So we have inputs, what goes into the model. So in our case, we have image tensors or batches of image tensors. And then we have outputs. So what comes out of the model / layer / block. In our case, we want the model to output image classification labels. Now that may vary per problem, but we're focused on Food Vision Mini at the moment. And then we have layers, which is every deep learning neural network is comprised of a number of different layers. And so it takes an input, manipulates it with a function. And the function, for example, could be self-attention, which is what's inside the vision transformer. And then we're going to have blocks, which is a collection of layers. And then we have a totem model, which is a collection of blocks. Beautiful. So spend a little time revising that and just have a look. The homework for this video is to just have a look at this for 2 minutes and read through it, and then just step through it and follow the arrows through. So do that 2 minutes, and then we're going to go through this a little bit more over subsequent videos. Or in fact, the whole entire section is about reproducing this with PyTorch code. So we've got inputs, outputs, layers, blocks, model. Let's make this colorful, hey? I'll see you in the next video.